Hello, everyone. I'm Anup Kumar. I'm a researcher working with the Bioinformatics Group and Freiburg Galaxy team at the University of Freiburg, Germany. In this talk, we will be discussing classification in machine learning. What is classification? Classification, as the name suggests, is to find different classes or categories in a data set in an automatic way. Machine learning provides various methods for doing classification tasks. One classification tasks example is to find whether a person has cancer or not by training a particular classification model on DNA methylation dataset. A class, as I said, is a category. It can be represented in machine learning models as different integers. For example, 0, 1, 2, 3. With the cancer and no cancer example, we can say that whether a person has cancer, then that class can be represented as 1, and no cancer class can be represented as 0. These are also known as categorical variables. In this classification tasks, the machine learning models have the supervision of classes, and they learn a mapping of the features with the classes for training itself and try to minimize an error between the true classes and the predicted classes. The classification task can be of two types. It could be a binary classification when there are only two classes, cancer or no cancer, for example, or a spam email or no spam email can be another example. It can also be multi-class classification when there are multiple categories in the dataset. For example, one popular example of multi-class classification is handwritten digit recognition. When we have multiple images of handwritten digits and the classes, the digits actually in those images can range from 0 to 9. Then we have here 10 classes. And machine learning models applied on this task learns to predict these different classes. In the example here, we can see there are two classes in a data set, the blue circles and the red crosses. And there is a decision boundary, which is red in color, which is learned, and the green one is the ideal decision boundary. In the second example on the right, we can see that the green one stays as the same, which is the original decision boundary. But when a decision boundary is learned using an automatic method, sometimes it could also be dependent on the outliers. We see that some of the blue examples here, they are outliers, and because they are very far away from the original blue circles. In this case, the decision boundary could differ from the ground truth decision boundary and may lead to higher errors in classification. But these are two details about classification tasks. Let's look at different models for classification. First, we look at a very simple model, is a linear model. In the image here, we can see we have two axes, x1 and x2, and a data point which contain two features, x1 and x2, can be represented as x. And then x could lie anywhere in this space. Then the model learns the weights. These weights can be represented as W0, W1, and W2. W0 is a bias weight. W1 and W2 are the weights for the features x1 and x2. And W naught, which is a bias weight, is the intercept here. And as I said, W1 and W2 are the weights for the features. They are also known as feature coefficients. We learn a function y, which is in terms of x1, x2, and W1 and W2 to create a decision boundary for two-class problem. Here, the decision boundary can be given by this equation yx equal to 0. When we have such values of x that sets this equation to 0, then classification boundary is represented by that. And our model, a linear model, learns this equation. When we have a point for which the value of y of x equation becomes more than 0, then it becomes class 1. Then if we have a point, let's suppose here, and for this y is positive, then the values of x1 and x2 could be at this point, and then for this point the equation becomes 0, more than 0, and then it's assigned to class 1. However, when the points for example fall here somewhere, then the value of y becomes less than 0, then that new point becomes a part of class 2. That is what the decision boundary does. It tries to classify a new point into two categories, class 1 and class 2. Then we have a support vector machine. Support vector machine is more complicated than a linear model. It has two variants, linear and nonlinear variants. The core principle of support vector machine is that it learns a decision boundary with maximum margin. What does it mean? When we have a decision boundary, for example, represented by the red line y equal to 0, then the distance between the examples which are closest to the decision boundary for both classes, here the decision from this point to the decision boundary and this point to the decision boundary. So these distances are maximized so that y equal to 0 line falls in the middle, and it's at a maximum distance from both the classes. This is the core principle of support vector machine. For classifying new points, it needs only the help of support vectors. Support vectors are the points that are closest to the decision boundary for any class. For example, if we have this distribution of decision boundary and the data points, then for the blue cross class, the support vectors are circled in green. For example, this becomes the support vector for class blue. These, because the black line, which is bold, this is the class boundary that separates between the red and the blue class. Then for the red class, these circled red crosses become the support vectors. And using these support vectors, new points are classified. All other data points can be thrown away. They are not needed for classification. In that case, support vector machines become more efficient. Another approach is nearest neighbor approach. Whenever a new example comes in, then the model tries to find out of k nearest neighbors of a new point, what is the class distribution. For example, if a green circle comes here, then what could be its class? If I follow an approach of 3 nearest neighbor, for example, then 3 of its nearest neighbors are one is blue square and 2 are red triangles. Since we have taken only 3 neighbors of green point here, then the class of the green point becomes a red circle, red triangle. When we take a bigger number of neighbors, for example, 5 here, then the entire range of neighbors would become represented by the dashed circle. And then we see that there are 3 neighbors of green dot, which are blue squares, and there are only 2 red circles. Then the class of this green circle becomes the blue squares. Let's look at decision tree. Decision tree works by learning decision rules from features. For example, in this image, we can see that we want to identify if a person is fit or not. Then the first feature that is used is age. If age is less than 30, then go towards left. Otherwise, if age is greater than 30, then go towards right. Then it utilizes another features. If age is 30 and whether the person eats a lot of pizzas. If it is no, then the person is classified as fit. And if a person is eating a lot of pizzas and still less than 30, then the person is deemed as unfit. On the other branch of the tree, when the age is more than 30, if a person exercises regularly in the morning, then this becomes a feature that determines whether a person is fit or not. And if it is no, and age is more than 30, then the person is deemed as unfit. These are the simple rules decision tree learns by utilizing different features from the data to classify a point. To classify a new point, then the decision tree has to traverse along one path from the root until the leaf. And that makes decision tree very efficient because the prediction is now logarithmic in terms of number of data points because it needs to traverse only a path in the decision tree to classify a new data point. It also is very interpretable. It's easy to understand. These are simple decision rules. And decision tree works for both categorical data and numerical data. For example, categorical data could be, for example, like when you have different categories in a feature. Numerical data is like values of temperature, for example. However, decision tree has a few advantages. It overfits quite a lot, and because it captures specific patterns from the training data, which is not very general, and tries to make decisions based on those specific features. Then the features which are not very general, if those are not learned, it tries to produce high accuracy on training data and lower accuracy on the test data. Decision tree is also sensitive to small changes in the training data. If training data changes, then the results could be very different. And it can be termed as a high variance in the output of decision trees. The disadvantages of a decision tree is mitigated by using a collection of decision trees. where each decision tree make a prediction, and then the final prediction is based on the average prediction of the X number of decision trees, or an average prediction of these many decision trees, or taking the majority voting. This kind of implementation of a decision tree becomes an ensemble method that we can see here in this line. It combines multiple tree estimators, and the prediction of each estimator is taken into account for making the final prediction. There are two approaches to an ensemble method, bagging and boosting. In bagging approach, average prediction of several estimators are taken, and when these estimators are trained in parallel, then they are independent from one another, and they make each prediction, and then a final class is taken from each estimator's performance. For example, here we can see that there are 5 different estimators, and each estimator produces a class, whether it belongs to class 2 or class 1 for a classification task containing 2 classes. Then we see that majority 3 of 5 models say that a particular example is class 2, then the final predicted output becomes class 2. Examples of ensemble method are bagging classifier or regressor, or random forest, which you might be familiar with. There's another type of ensemble method. It is boosting. Boosting is a sequential approach in which many weak learners are learned, and then each weak learner, which is a tree estimator, gets improvement in a sequence, and then it makes more improved estimators sequentially. Since this is sequential, it cannot be executed parallelly, and it takes more time for a model to do classification or regression. Examples of boosting approach is AdaBoost, classifier and regressor, and gradient boosting as well. In this talk, we discussed briefly about what a classification is, and then we looked at several classifiers, from linear ones to complex ones. Linear ones are very fast, but many times the data is not linearly separable. So linear models may not work, and we need to go for more complicated approaches such as support vector machines, or nearest neighbor approaches, or even ensemble methods. Now we will go to the Galaxy tutorial for classification, and then we will do a hands-on with a certain classification data set. Thank you.